Okay, we want to title these EMR notes. EMR is an abbreviation for the big fat word electromagnetic radiation, which is a big hairy word. It really just means light in one form or another, and that's what we're going to look at. And the cool thing about light is it has, we call it the duality, but it has a dual character. Light does. Oops, spelled that wrong here. Dual character. So that means that it has properties that makes it behave like a wave, and it has properties that make it behave like a chunk of stuff, a particle. They call it a particle nature and a wave character. So there you go, kind of in a simple way. We are going to look at the wave nature of this. So if we just draw a typical wave structure, something like this, which we've seen before, certainly, we can identify some different parts. Identify a stretch from here to here, which we call a wavelength, and then we can identify this area, which is a crest. We can identify a trough. We can identify the region from one crest to another crest, or a trough to a trough, and we can identify that as a wavelength. It's a distance, crest to crest or trough to trough, either way. We could put a center line on here, lots of stuff we could do, and we could talk about the amplitude. Okay, I've redrawn the waveform you can see here. You can just use the one you already have on there to imagine this. But I want to talk about a couple different things. One is all light travels at the same speed. So travels at the same speed. So, I mean, it could ask you to make a wild guess at what that is, and so you might make a wild guess that light travels at the speed of, you guessed it, the speed of light. So now the interesting thing, if you examine these waveforms here, the crest to crest and the trough to trough and that kind of stuff, since light is moving at the same speed, it's all traveling at the same. That's important, because when we start to talk about frequency, let's write frequency. Frequency is how often a wave crest or wave trough, we'll just talk about a crest, a wave part, passes a particular point in a particular time. So frequency is measured in cycles per second. Okay, that's what frequency is measured in. Now that's a cool thing. So for a light wave, since it's all traveling at the same speed, so you can imagine a different kind of wave. If the frequency is going to be strongly dependent on how fast the wave is moving, because the faster it's moving, the higher the frequency, the quicker that a particular wave crest is going to be passing a particular point. Since they're all moving at the same speed, if this space between them is all identical, then they would all have the same frequencies. But it turns out light waves aren't like that. There are light waves that have very long waves, and then there are light waves that have short wavelengths, very short. So that's a short wavelength, that's a long wavelength. And it turns out that the number of cycles per second, which we call a hertz, and we'll write that down here in a second, identifies the character of the different forms of light that we can observe. So one cycle it's a Y, sorry. Cycle per second is 1 hertz. Okay, now it turns out music waves, audio waves are also measured in hertz, and we're talking about a frequency there, and they typically move in the same medium. They'll move at the speed of sound. So sound waves, they're a different kind of wave, they're a compression wave, but nevertheless, we can still use them as kind of an analogy for this, and you can think of bass waves as being very long wavelength like that, and higher pitched waves. So for sound waves, it's the same sort of deal where you get this wavelength that's representing the distance between here and there. We are going to talk about the electromagnetic spectrum. Electromagnetic spectrum, which is in your book on page 585. So I'm going to do the best I can to kind of represent that diagram in our notes here. I'm going to draw a little square, and we're going to make a kind of a simple version of that electromagnetic spectrum. So I'm going to draw as best I can, kind of represent the whole thing there. We're going to start on the left with some really very wide frequencies, and then eventually go to where very, very high frequencies to very, very low frequencies right there. So we're going to give a couple labels here as we do this. And we're going to call this, these are long waves, and these are short wavelengths. They're not waves, they're wavelengths. I spelled that. So, lengths. These are short wavelengths on this side. This is a continuum. Wavelengths. Okay, and so what we're going to do is we're going to start with, at the very far end, the longest wavelengths in the electromagnetic spectrum are radio waves. We go from radio to microwaves. So microwaves have just slightly shorter wavelengths than radio waves. Infrared radiation right here, and then visible light is what we can actually see is right kind of in the center here. At least we're going to put it in the center, and it looks kind of like this. It's usually drawn something like this, kind of in the middle. That book actually does a better job. But then we can see that on one edge here we've got kind of the reddish side, red Roy G. Biv thing, and on the other side we have more the blue part of the visible light, what we can see. And so there's all the colors of the rainbow in there, and so we've represented that as best we could. So this is called visible light. That's what we see. Oops, it's not very good. Doing my best here. Write the word visible a little bit better. Visible light. Okay, that's supposed to be an S. All right, and then on this side we get ultraviolet, X-rays, and gamma radiation. Extremely short wavelengths, extremely high energy. So gamma rays. So short wavelengths. This has very low energy, very, very, very high energy on this side. All right, just some miscellaneous stuff to help you out on the final here. We'll call this miscellaneous stuff, kind of related to what we were just talking about. I just want to mention that the first stage in the space program, designed to send Americans to the moon, was actually Project Mercury. It was the first stage in the space program designed to send Americans to the moon. The first stage. Of course, Apollo was the big guy, but there we go. Light pollution is oftentimes allows only the brightest stars to be visible. So light pollution is a major problem on Earth, from city lights that prevent us from actually being able to see stars and other stellar phenomena. Miscellaneous factoid: Neil Armstrong was the first human to set foot on the moon.